Mountain Math set number 17 today. Alright. One of the most famous drum loops on the planet right there. Alright, boys and girls. So, set number 17, we are going to be looking at 12 problems today in this Mountain Math video. And I have already set some of them up to help us move through this so that it's not a 45-minute tutorial for you. Our two numbers for set 17 are appropriately 17,888 and 17,880. We have this sneaky question here, even or odd. Remember, kids, looking at the ones place, you have an 8 in the ones place and you have a 0 in the 8th place. In the ones place, both of those digits are even. Because the even digits are in the ones place, it makes the entire number even. Both of them are even there. 17,888 in word form, 17,880 in word form. Both of the numbers here expressed in expanded form. Let's see, any points here looking at 17,880 because there's a 0 in the ones place. You do not need to add a digit for the ones place. You do not need to put plus 0 here at the end. Okay. Adding 100 and taking 100 away. This problem's pretty straightforward. Because there isn't a 9 in the hundreds place, we're not going to have to worry about changing the hundreds place to a 0 and then the thousands place going up one digit. Here, when we add 100 to 17,888, we get 17,988. When we take 100 away from the same number, 17,788 is where we end up. We're either adding one digit to the hundreds place or taking a digit away, depending on if you're adding 100 or subtracting 100. Similarly, over here, 17,880 plus 100, you're going to boost the digit in the hundreds place up 1. So we now end up with 17,980. And if we take a digit away, if we take 100 away from 17,880, we are going to decrease the digit in the hundreds place by 1, therefore ending up at 17,780. Okay, the next three scenarios we are put in with this number, we are to multiply by 10, 100, and 1,000. Anytime you're multiplying a number by 10, 100, or 1,000, just write the number out and then add the appropriate amount of zeros. Appropriate meaning for 10, you're going to add 1 0 because there's only 1 0, and 10, you're going to add 2 zeros if you multiply by 100 because there's 2 zeros in 100, and similarly 3 zeros when multiplying by 1,000. So we can go ahead and do that and add our commas appropriately. So we are at 17,888. Now we're going to multiply it by 10 simply by adding a 0. Ones, tens, hundreds, comma. By multiplying by 10, we end up with 178,880. The power of the 0, my goodness. 17,888 times 100, we will add 2 zeros, ones, tens, hundreds, comma, ones, tens, hundreds, comma, 1,788,800. The difference that 2 zeros makes, my goodness. And at multiplying by 1,000, we are going to add 3 zeros. Ones, tens, hundreds, comma, ones, tens, hundreds, comma, and 17,888,000 is where you end up. Okay, over here, we're going to add a 0 when multiplying by 10, ones, tens, hundreds, comma, 178,800. Add 2 zeros when multiplying by 100, ones, tens, hundreds, comma, ones, tens, hundreds, comma, 1,788,000. And then we will add 3 zeros when multiplying by 1,000, and we end up with 17,888,000. 880,000. All right, so comparing these two numbers. Now, when we're comparing these two numbers, we need to find the first digit place value position that has a different digit. So we're looking at the 10,000s, same. 1,000s, same. Hundreds, same. Tens, same. Finally, at the ones place, we have a spot where the digits are different. 8 is greater than 0, making 17,888 greater by only 8. 17,880. How many ones are in the tens place of 17,888? Well, we have an 8 in the tens place. That makes it 80. How many ones does it take to make 80? Well, 80 ones. How many tens are in the hundreds place? Well, we have an 8. The value of the 8 there is 800. How many tens? 10 times what equals 800? And that's 80. How many ones are in the tens place? Well, we have another 8, so it's 80 ones. And then in the hundreds place, the digit's the same, so we can essentially copy 80 times 10 is going to get us the 800, which is the value of the 8 in the hundreds place. Okay, all righty, moving on. We're looking at number 2 here, 432,860 is the number that we're working with today. And we need to write down the value of the 8. The value of the 8 in this number, because it's in the hundreds, it is 800. The value of the 3, it's in the ones, tens, hundreds, comma, 1,000, 10,000s place. 30,000 is the value of that 3. Now we need to round these numbers. Here we need to round to the nearest tens place. Well, if we look for the digit that's in the tens place, it's 6. Okay, so we need to round 60 to the nearest tens place. And guess what? It's already rounded. And we know that it's rounded because there is a 0 in the ones place to the digit to the right of the number that we're rounding, either up or down. So we can simply write the number as is because it's already rounded for us. Now the thousands place. The 2 is in the thousands place. So when we're rounding this large number to the thousands place, we're really thinking about what is 2,860 to the nearest thousands place. And our only options are 2,000 or 3,000. Now, 2,860, is that greater than 2,500? Yes, it is. That means that 2,860 is going to be closer to 3,000. So, because it's closer to 3,000, it makes the number 433,000. Okay, now the millions place. The millions place, it's funny when we do these problems and there's not even a digit in the millions place. Well, there is actually a digit in the millions place, and that is 0. Now we're asking ourselves, is this number greater than 500,000? And no, it's not, because there's a 4 in the 100,000s place. That means that this number rounded to the millions place, it's actually closer to 0 than it is to 1 million. Okay, so rounded to the nearest millions place, unfortunately, that 0 stays the same. 4 or less, let it rest. There it is. Okay. All right, number 3. Number 3, we need to find out, is it a prime number? And immediately, I know it's not a prime number because I know a basic fact that equals 45, and that is 9 times 5 is 45, and likewise 1 times 45 is 45. So this number is 100% composite. It is made up of factors 9, 5, 1, and 45 that are more than just 1 and itself. So number 3 is composite. Okay. Moving on to number 4. Number 4 is our greatest common factor, and we need to find the greatest common factor of 49 and of 42. So as I am looking here for my multiplication table that goes to 15, because I know that one's going to help me out pretty good, more than the 12. So I need to list the factor pairs of the number 49. So I do know some immediately. 1 times 49 and 7 times 7. Now we need to see if there's any more. So essentially we are scanning for 49s in this multiplication table to find some factors. And we might look more or less at 13, 14, and 15 as a possible factor. So let's scan. There's 39, and then straight to 52. Nope. 14, we have 14, 28, and 42. Nope. And we have 15, 30, and 45. So, unfortunately, the only factors of 49 are 1, 7, and 49. How about 42? And I can say that confidently because I know the basic facts that do equal 49, and that's 7 times 7 and 1 times 49. And then I'm thinking like anything times 9, 9 times 5, 9 times 6 is 54. So nope. I'm thinking 10, definitely not. 11, no. 12, no. So we are left with 1, 7, and 49. Now the factor pairs of 42. We know we have 1 times 42. We know it's an even number, so 2 times something equals 42, and that's 21. And I know that 6 times 7 is 42. So looking at the factors here, I've got the ones that I know. Now I can go to my multiplication table and I can check to see if there's any other factors of 42. 10, definitely not. 11, no, close. 44. 12, nope. 13, we got 39, then 52. Ooh, look at that. 14. 14 times 3 is also 42. 3s, 6s, 7s, and 8s can be tricky. So we always want to either use our multiplication table or long division to help us out with some of those more sneaky factors that equal the product. So now we have our factors of 42. We have 1, 2, 3, 6, 7, 14, 21, and 42. So now we need to circle the factors that are common. We have 1 in common, no 2s, no 3s, 7 in common, and we stop there. The greatest common factor of 49 and 42 is 7. And so if we wanted to take a fraction like maybe 49 42nds and put it into simplest form, 1, we'd convert it to a mixed number because it's an improper fraction. And then 2, to get the fraction itself in simplest form, we can divide both by 7. That's how we use the greatest common factor. Okay. Now listing the multiples. For number 5, we have 2 and 9. We got to list 8 of them. I'm going to end up at 16 for 2, and I'm going to end up at 72 for 9. So we have 2, 4, 6, 8, 10, 12, 14, and 16. I know that those are the multiples of 2 because on the multiplication table, in order to find the multiples, they're all inside here. I just need to find 2 as my factor and follow it along 8 times. Or I could do it vertically as well, 8 times. So now 9. We can go to our factor 9 here, or our factor 9 going vertical or horizontal to list the multiples. And we have 9, 18, 27, 36, 45, 54, 63, and 72. So I love the nines. In the ones place it goes, or in the tens place it goes 1, 2, 3, 4, 5, 6, 7. And in the tens place it goes in the opposite, decreasing 8, 7, 6, 5, 4, 3, 2. And then if you wanted to list that ninth factor, 1 and 8. Okay, I like that pattern in the nines. Okay, complete the pattern. 1, 2, 4, 8 is what we were given in number 6. And so we're going to look at this. We're going to look, how did we change from 1 to 2? Do we add 1? Could be. What do we do to 2 to 4? Do we add 1? Definitely not. So likely it's going to be multiply by 2. By 2. Okay, look at this, 4 to 8 by 2. So now we can ask ourselves, well, what's the next number in the pattern? If the pattern rule is multiply by 2, we can keep going. What are the features of this pattern? Are there shapes? Is it numeric? Is it non-numeric? Well, because there's numbers involved, it is a numeric pattern. And then we can find out the 10th and 15th after we've found the first 5 in our pattern. So 8 times 2, our next number is going to be 16. 16 times 2, well, 10 times 2 is 20. 6 times 2 is 12. 20 plus 12 is 32. 32 times 2, we're just doubling these numbers, and so you could be adding 32 plus 32 mentally, or you could be using the multiplication algorithm, but 32 times 2 is 64. 64 times 2 could be 64 plus 64, or 64 times 2 will end up at 128. And now 128 times 2, we could do 128 plus 128, or 128 times 2. Since this is a 3-digit number times 1, we may as well work out the algorithm, as this is a very important skill for you to walk away from the 4th grade with. 8 times 2 is 16. That's a 2-digit number. Put it over here, circle it. Got to do something with it. Put down your 6, carry your 1. 2 times 2 is 4, plus 1 is 5. 1 times 2 is 2. 128 times 2 is 256. So, what is the 10th number in this pattern? Now, we've got some options. We can multiply 256 times 2, and that answer 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 times 2, or we can multiply 256, okay? Because it's the 5th number in our pattern that we found, we can take 256 times 2 and multiply by 10. So 256 times 10, we just add 1 0, 2,560, and then the 15th number in this pattern. So we are essentially multiplying 256, what we know, okay? We can multiply it times 15. We could keep multiplying it times 2. But in this case, we can take 256 and multiply it times 15. How can we do that? We don't multiply 3-digit numbers times 2-digit numbers. Well, in this case, you have 256 times 10, okay? And we know that that's 2,560 plus 256 times 5, and we end up with 6 times 5 is 30, 2-digit number, circle it, got to do something with it, put the 0, carry the 3, 25, 28, 10, and 12, plus 1,280, and we end up with a 0 in the ones place. We end up with a 4 in the tens place. We end up with an 8 in the hundreds place, and a 3 in the thousands place, 3,840. Okay. All right. Number seven, we are going to refer to our document here that I provided with the numbers, and we have a situation. Ron has 8 slices of orange. Jill has 2 slices. How many times as many orange slices does Ron have than Jill? Well, Jill has Ron has 8. Okay. Jill has 2. How many times more slices does Ron have at 8 than Jill does at 2? Well, 2 times what is 8? And that is 4. Okay. So Ron has 4 times as many orange slices as does Jill. Okay. Number 8, lasagna. Lasagna is actually what that is. And we got a young lady, Erin. She made a bunch of lasagna, man. She made 4 pans of this stuff, and she cut each one of those pans up into 12. So I drew that picture. Okay, for me, drawing pictures is a way for me to better understand math. So I drew the 4 pans, and I made sure that there were 12 pieces inside of each one of those pans that were as equal as I could possibly make them when drawing a picture. How many total pieces of lasagna are there? We've got a couple options here. We can count them all. 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Now that gets old. But we know we got, after 2 pans, we got 24. 12 times 2 is 24. So if I multiply 12 times 4, I should get all my slices. That's 48 total slices. So essentially, that is 48 twelfths. Okay, that is what that fraction is right there, 48 twelfths. If Aaron's friends ate 37 twelfths pieces of lasagna, how many full pans were eaten? How many pieces are left? Well, we know we got a total of 48 pieces, of 48 twelfths. The friends ate 37. So we could fill in this whole grid. That's 12 slices eaten. This is 24 slices eaten, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37 twelfths. There is our 37 twelfths pieces eaten by the friends. How many total pans? This is tough. How many total pieces of lasagna are left, and how many full pans were eaten? Sorry, I had a hard time reading that. Well, how many full pans were eaten? How many did we cross off? 3 total pans. Okay. And how many pans or pieces are left? Well, we don't have a full pan left, but we do have 11 pieces remaining. Oh, wow. Let's just start over on that one. Remaining. There we go. All right. So, in this problem, drawing the picture is definitely the easiest route. But we could also look at this as an improper fraction, and you could have converted 37 twelfths into the mixed number that it is simply by asking yourself, 12 times what is close to 37? Well, 3. Okay? And that's your whole number, 3. And how many are left to get to 37? 1, and your denominator stays the same. So eaten were 3 and 1/12 pan of lasagna. Okay, that's another way to look at this problem here. Right? Number 9. Adding and subtracting numbers. 5,555 plus 606. I have 11, 6, 11, and 6. 6,166. Subtracting them. Well, I got a bunch of 5s across the top, and I have some 6s. I know I'm going to be regrouping. Start over here at the thousandth place. I'm going to borrow 1,000 from the 5, leaving 4 thousands left. I'm going to regroup that so that I have 15 hundreds. I am going to look at this 5. I can do this problem, 5 minus 0, but I need to borrow here, so this 10 becomes a 4 instead of a 5, and then I add those 10s to my 1s and end up with 15 ones. Now I can subtract. 15 minus 6 gets me 9. 4 and 0 is 4. 15 and 6 is 9. And 4 and 0 is 4. 4,944. Okay, great numbers. I like seeing that alternating digits when adding and subtracting. Multiplying 420 times 7. I get 0. 2 times 7 is 14. Two-digit number. Put it over here. Circle it. Got to do something with it. I'm putting that 4 down, and I'm going to carry the 1. 4 times 7 is 28. Plus 1, 29. 2,940. Now long division. 420 divided by 7. I cannot divide 4 divided by 7. 4 is smaller than 7, meaning I need to immediately go over one digit and look at this problem as 42 divided by 7. That would be 6. I get 42. Then I subtract, and I bring down my 0. My new problem is 0 divided by 7. Anytime that's the case, just put the 0, multiply, subtract, you're done. 60 is the quotient. 420 divided by 7 equals 60. Just as 42 divided by 7 would be 6. You tack on those zeros, 420. You have to tack the 0 on to the answer on the quotient, making it 60. Fill in the missing number. 149 minus something is going to be the same as 149 minus 7 minus 10. How much are you subtracting in all from the right-hand side of the equal sign? Will tell you what to take away here. It looks like we're taking away a 7 and we're taking a 10. So the missing number in this case is simply 17. If we're going to take 17 away from this 149, we need to take 17 away from this 149. Okay? All right, number 12. Number 12, oh, Mr. Fraction. 7 eighths and not 8 ninths. I like this one. It's great because I'm going to be able to find my answer on the table. I have 7 eighths and I have 8 ninths. So I'm looking in this realm here. Eighths and ninths. If I have 7 eighths, each one of those fractions is only 1 away from the denominator. You would assume that they are exactly the same, huh? But that's not always the case. Rarely is it the case. If I have 7 eighths, 1, 2, 3, 4, 5, 6, 7, that puts me there. And if I have 8 ninths, I have 1, 2, 3, 4, 5, 6, 7, 8. That puts me there. Being 1 away from the denominator sure makes it close, but they are not the same. They are not equivalent. Now I'm looking at this table here. I'm going to say that 8 ninths is greater than 7 eighths. 8 ninths is greater than 7 eighths, or 7 eighths is less than 8 ninths. Are they equivalent? No, they're not equivalent. We need to make them equivalent. This is where we have to use least common multiple. And we're going to use least common multiple so that we can get our denominators to be the same. So we have 7 eighths and we have 8 ninths. We're going to list the multiples of 8 and 9. And I'm just kind of getting ready here. to use my multiples. That's why I've drawn these boxes here. Okay, this is actually set aside for a multiplication sign. What are we going to multiply 8 and 9 by so that we can get the same exact denominator? So let's list the multiples of 8. We have 8, 16, 24, 32. Still haven't hit one that is similar to 9. I'm going to go 40, then 48. I still don't think I've hit one that's equivalent to 9. We're now going to go 56. Then we're going to go 64. Still nothing. Now 72. I think 72 is also a multiple of 7. So it looks like we're going to end up with a denominator of 72, but let's list our multiples of 9 just in case. 9, 18, 27, 36, 45, 54, there's no comma there, 63, and 72. The least common multiple of 8 and 9 is 72. Now, why do I got these boxes here? Because what am I going to multiply times 8 to equal 72? What am I going to multiply times 9 to equal 72? I am now going to multiply 8 times 9 to get 72 and 9 times 8 to get to 72. Whatever I do to the bottom, whatever I do to these denominators, I've got to do to the top. 7 times 9 is 63, and 8 times 9 is 72. Excuse me. 8 times 8. We want to multiply the same 8 and 8, and we get 64. So we have 64 70-seconds and 63 70-seconds. How do we make them equal? You got two options. You can either add 1 to 63 to make 64, or you can add a 70-second to subtract a 70-second to get to 63. So 63 70-seconds plus 1 70-second equals 64 70-seconds. Okay, so we went the route in order to make them the same. We wanted to make 63 70-seconds the same as 64. You couldn't do the opposite. You can make 64 70-seconds equal to 63 70-seconds by subtracting. I went the addition route. We're not done. We need to put this into simplest form, greatest common factor. What are the factors of 64? We have 1 times 64, 2 times 32 is 3, a factor of 64. Well, to find that out, we could have our multiplication table. And let's see. 3, we get to 45 plus 15 more is going to be 60. Then 60, no, doesn't work. 8 times 8. 8 times 8. Let's look at 4. Does that make 64? Oh, yep. So it looks like if 4 times 15 is 60, that means 4 times 16 is going to be 64, because 4 more than 60 is 64. So we have 4 times 16. That equals 64. Now we can look at 5. Nope, got to have 5 or 0 in the ones place. We can look at 6. We got 60 and 66. Nope. 7, 63 to 70. Nope. 8, we already got 8 times 8. 9, 63 to 72. Nope. 7, 60 to 70. 55 to 66. 60 to 72. Nope, just not seeing 64 again. All right. We are going to assume that we have found the factors of 64, which are 1, 2, 4, 8, 16, 32, and 64. Now the factors of 72. We have 1 times 72. It's an even number, so 2 times 36. We can see if 3 times anything gets us 72. Let's do a little long division to find that out. 72 divided by 3, we have 2, 6 is 1. Bring down the 2. Oh, yep. 12 divided by 3 is 4. 3 times 24 is a factor pair. I'm going to get a little squished here. Let's take a look at 4. Anything times 4 get us there? We have 64, we have 68, and we have 72. Let's do a little long division here. Let's do 72 divided by 4. We get 1. 32 divided by 4 is 8. Yes, 4 times 18 is a factor pair of 72. Using long division to find those sneaky factors is going to help tremendously, okay? And when we do that, we make sure that we're complete. Now we can take a look at 5. No, definitely not. 6, we have, 6 times 12 is 72. I'm going to get a little out of order here because I'm running out of room. How about 7? 7, we got 7 to 77. Nope. 8. Yep, of course. We have 8 times 9. Okay. 10, no. 11, no. 12, already got it. 13, nope. 14, nope. And 15, nope. Okay. We can assume that we are complete in finding the factor pairs of 72. So let's list them. We got 1, 2, 3, 4, no 5, we got 6, no 7, we got 8, we got 9, and we have 18. Well, 6 times 72, that is not what I meant to write there. I meant to put 12. Turn that into a 12. Looks like a 12. Okay. Then we have 24, 36, and 72. All right. Greatest common factor. Well, we've got 1s, we've got 2s, we've got 4s, we've got 8s. We've got 16s, nope. We've got 32s, nope. We got 64s, nope. We are done. The greatest common factor of 64 and 72 is 8. 64 divided by 8 is 8. And 72 divided by 8 is 9. And we go all the way back to, in simplest form, 64, 70 seconds is 8/9. All right, that is number 12. My goodness. We used the fraction strips to determine if they were equal. Looking at the 8s and 9s, they were so close, but they're not equal. And then we made them equivalent by finding the least common multiple, which was 72, changing our fractions. And we wanted to make 63 70 seconds the same as 64 70 seconds. So we added 1 70 seconds. That's what it asks you to do. If not, make them equivalent. It's more or less telling you what to do. So we then put our answer into simplest form by using the greatest common factor and using long division as a strategy to help us not miss any sneaky factors. 3s, 4s, 6s, 7s, 8s. those are rather sneaky factors. And so we've got to use long division to help us determine that. Okay. All right. Mountain Math set number 17. That was a doozy. So I appreciate you following along with me. And I do hope that you enjoy your day, your evening, your morning, whatever time it is that you might be watching this. Okay. All righty, kids. Y'all take care.